Can I go? Yeah, okay, so hi everybody. I'm Filippo Vicentini from the Computational Quantum Science Lab in EPFL in Switzerland, and I would like to present you the Netket. So the idea of Netket is essentially that, I mean, maybe you've seen a bit that like we love quantum computing, right? Like the idea of being able to exploit the quantum nature of physical systems to directly represent like those highly complex states. The idea is that we can do a lot of calculations. We could simulate systems that we're interested in, but of course, let's say quantum computing is still not there yet completely. So some of us started to think that actually machine learning is a great tool and a very powerful one, right? So basically, machine learning is able to compactify and compress information found in some data. For example, you can take some images that are very large and have a lot of data, and you can compress them down to very few bits of information, and then reconstruct the original image at the back. And so some physicists a few years ago had this idea of why not trying to use was very same neural networks that we're using for pretty much everywhere in the cloud nowadays to actually do some physics while we don't have yet a quantum computer, and maybe also to give some challenges to quantum computing. And therefore we tried to build this software. So Netket is kind of a toolbox. We were featured a year ago, a little bit over a year ago on Nature reviews, because essentially what Netket tries to do is to allow us physicists, and not only physicists, also chemists and other scientists, to take ideas from machine learning and apply them to quantum many-body physics. So the idea is very simple. You have those kind of machine learning libraries like JAX, TensorFlow, PyTorch, and others, but they don't speak at all the same language of physicists. So like you have projects like QTIP, OpenFermion, or like you have your own Hamiltonians that you want to study. You have your own physical problem that you want to study. And Netket is trying to be this man in the middle that is connecting those two worlds. At least that was the idea we had at first. Nowadays, we had to refocus a bit, so we are focusing now only on JAX, on one of those libraries, the one that we think has a very bright future. And nowadays, essentially, what we do is we are trying to connect JAX with quantum physics. So I would like to give you just a quick demo of what you can do with Netket. Essentially, you can, for example, it's a Python package as pretty much everything else, and the key point is that you can construct some system. So let's say you want to specify a system of spins. Let's say we want to study a system with 20 spins, right? And this we know, if you know some quantum physics, this has a very large space of almost. Okay, my computer froze. This has a space of almost 1 million configurations. So I would need to store the configurations to store more than 1 million configurations to actually represent the system. Instead, with Netket, what we do is that first we try to define some approximation. Let's say, for example, we take some restricted Boltzmann machine, which is a very simple neural network with real parameters. And we define some scheme by which we select only a small part of the Hilbert space. This would be the sampler. So essentially, we use some metropolis sampling techniques. And then we can put everything together in what we call the variational state, which is this object that tells us how to sample the whole Hilbert space and has some very well-defined neural network architecture. And now instead of having to store more than 1 million parameters, we only have to store 440 parameters. Of course, this is an approximate method, so it will not always work. It will not always give us the right solution, but in some cases it can. And so if I take a very simple Hamiltonian, such as, I don't know, the Ising model, if you are a physicist, you're familiar with that. If you're not, that's a very prototypical problem studied in quantum physics. So I'm taking a transverse real Ising model defined on those 20 sites. And then I can simply try to run this optimization using some very standard machine learning optimizer with a very standard learning rate. And if I run that, okay, live demos are always hard. So if I run that, it will take some time. There's always some stress when you run a live demo because it might not work. Yeah, and that's exactly what is happening right now, I think. Yes. So okay, I will switch to the website of Netket to show you what happens if it works. If we are able to work, you will be able to look at some observables of your system, for example, the energy or anything else, and you will see that it slowly converges. So basically what we are doing is we are recasting our quantum physical problems into machine learning problems through Netket. And so to go back to the unitaryHACK, essentially what we are opening a set of bounties, kindly sponsored by the Unitary Fund. We are looking for contributors both in the field of physics, so both physicists or people that know a bit of linear algebra, and also for people that don't know any physics at all. So we have some bounties for someone to add some more logging things using some more advanced formats like HDF5. We would like someone to add some colors to our outputs so that we use red when some outputs are very bad to draw the attention of users, and while green when those values, those indicators are saying that everything is fine. And then we are looking also for some physicists and people with some physics background to implement support for more general operators, because right now, for example, we only support some specific Hamiltonian, some specific operators that are not too large, and we would like to extend that. And we are also looking for people that know a bit about statistics to implement support for streaming, single pass statistics. And of course, we have also many other projects. We are looking forward to participate in Google Summer of Code next year. And sometimes we have some students that come around and work on bigger projects that take much longer. But of course, that's not the focus of the unitaryHACK. So if you head up to our website, we list on the Get Involved section a few ways to get in touch with us. We have a Slack channel. We monitor the Discord of the unitaryHACK, and you can, of course, contact and talk with us on GitHub, where we're always very active. So we are really looking forward to finding and meeting some new contributors to join the project. And thanks for listening to me.
Thanks, Filippo. Another very exciting project.